Hey there, this is Final Exam Screencast question number 4. My name is Kevin Reynolds, and we're going to jump into it real quick here. Alright, so quick rundown of what we're going to go over. We're going to look at fluorescence anisotropy. We're going to lead that into depolarization, kind of what that is. We're going to look a little bit at dissociation, and then round off with NMR and how it kind of relates to some of the concepts we're going to see in fluorescence anisotropy. So to start, what is fluorescence anisotropy? Now, because it's a mouthful to say, we're going to refer to it as FA from this point on. One of the biggest factors going into FA is the concept that size matters. So what we're looking at is either proteins, as you can see on the bottom. Sometimes, especially the smaller one, can be replaced with ligands. They do the same thing, and we always look at the same stuff ultimately from it. So what we're actually kind of looking at is, in a sense, the rotation of these proteins or ligands as they interact with one another or stay on their own. So, kind of to give a little brief example of what we kind of look at, like I mentioned, it's rotation. So when we look at this protein here on the left, we're going to notice a couple of things. One concept is that it's going to spin faster. So to describe this, I'm going to place my little pointer right here, and we're going to think 1, 2, 3. That's all it goes around. If we were to do it on the same one over here, we'd go 1, 2, 3, and only make it about a quarter of the way. This is kind of showing how in FA, we see different rotation speeds. And what this ultimately does is we kind of want to look at, and it's going to start gearing us towards looking at how light reflects and deflects off of these and how it's actually picked up. Now, to kind of note, we're going to slide over here real quick and look at one thing, kind of in a really abstract way. But if you were to think of a molecule or a protein on the bottom versus a protein on the top, what we can actually do is probe the protein on the top with this red kind of hyperactive protein, if you will, or fluorescent protein, so we can see and indicate how that actually is going to affect it. What ultimately is going to happen is we're increasing size again. So in doing this, when we look at the small protein here on the bottom first, and we look at the spin and the rotation of it and whatnot, it's going to rotate extremely fast. What this actually does is has the light hit it and deflect quickly and readily and easily and very, very, very frequently. Ultimately what this does is it gives us a very steady reading that we don't see much difference in, and it also ultimately leads to what is considered depolarization. That is, light not being changed or altered, but at a stagnant and level rate. When we look at this top one, what we kind of see is as it were to rotate, we'd see different things on the actual structure and how light's going to deflect. So when we got to this side, this indent in the actual protein itself would reflect light a little differently, show up a little different, we'd be able to see different things. And with this probe on it, we'd actually get different results as well, as that would give off its own little piece. What's nice that we see in fluorescence anisotropy is we can actually get readings based on how things are spinning. So based on concentration of additional ligand or protein, as you can kind of see down here on the x-axis, we get a different FA on the y-axis. We get this kind of, in a sense, hyperbolic relation, which when referenced to other things and whatnot, when about 50% of it is kind of in a sense used up, or you get a 50% emittance out of your maximum, you get this kind of dissociation constant. What you can actually see is how when things split, they spin faster. When they combine and come together or associate, they spin a little bit slower. So that's one way that we can kind of get a dissociation out of it. Moving along, kind of briefly, we're going to discuss NMR and how that actually relates into the concept of small versus large molecules. It's looking at the nucleic rotation, which, in essence, to FA, rotation size matters. This, in a sense, as it rotates differently, it will relax a little bit less or a little bit more, depending, and we ultimately get this kind of correlation to small versus large molecules.